Hello, my name is Alexander Miramontes, and today I'll be presenting my Physics 2212 Lab 3 report. To start, the purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet and compare the measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. For the concepts used in Lab 3, the first are bar magnets, which are essentially magnetic dipoles in all cases, including this lab. The second is that magnetic fields of a dipole of an axis are also important to know. And lastly, that magnetic fields can be superpositioned, in which we can use this to remove magnetic interference, such as the Earth's magnetic field in this experiment. For the setup of this experiment, in the left diagram, the distances for different bx's are measured and then plotted. On the right diagram, we find the perpendicular distance needed for the magnitude of the magnetic field to be 100 microteslas. And then the net magnetic field is calculated at the spot shown in the diagram. This will be compared to the results of the computational model. On this slide, I have my raw data found for the lab. Here I have my net magnetic field that's 45 degrees off the axis from the dipole. And also here I have the graph of ln(bx) versus ln(r), and I used this data to do the needed calculations for this lab. The two equations shown were set equal to each other to get mu by itself, which would be 10 to the 7th power times k times r to the n plus 3 divided by 2. The data from my graph was used for these equations. N equals the slope of the graph, and ln k is the y-intercept. By using these values and the equation solved for, mu would equal to 3.1835 Newton meters per Tesla. Of the four statements shown, only the first and last were shown to be true. During the experiment, when the magnetometer was far from the magnet, the x direction had a near zero magnetic field. Also, when the magnetometer moved closer to the magnetic field in the x direction increased. After the physical experiment, I had to do a computational model. First, I defined a function for calculating the magnetic field due to a dipole with a dipole moment at an observation location. Then, arrows were added for the 6 of the 7 points, which were coded and used to visualize the magnetic field as seen from the previous slide. Then, the same process was done, but for the observation location at 45 degrees angle that's off axis from the dipole. For the model, the orange arrows are the two on-axis magnetic fields, the blue arrows are the perpendicular fields, and the purple arrow is the 45 degrees off-axis magnetic field. Below is the output, and where the magnitude of B at a 45-degree distance d is shown to be 2.86 times 10 to the negative 5. The two B net values are compared, the top being from the physical experiment and the lower being from the computational model. Both are different, but not too different since both are to the same power. This shows that there may be some interference and errors made, but regardless are somewhat close to each other. To answer the question, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The results would have been wrong for Bx by a specific amount because of Earth's magnetic field interfering with the experiment. The magnitude of the magnetic field would also change to be wrong and inaccurate. For the second question, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? Well, the measurements will be multiplied by a specific scalar value, essentially sort of the same results. The only difference for the experiment will be the magnetic dipole moment.